Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. InVideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello everyone and welcome to this lecture in the Build DeepSeek from Scratch series. Today we are going to start learning about positional embeddings. First, let me clarify why are we learning about positional embeddings or positional encodings in a course about DeepSeek. So, in the previous lecture, we learned about multi-head latent attention, and we have started this whole series with the purpose of understanding the DeepSeek architecture in detail, and ultimately with the purpose of building the different components of DeepSeek from scratch. So then suddenly, why are we starting to learn about positional encodings? Let me give you a little bit of a background around that. So here is the DeepSeek version 2 or DeepSeek V2 paper which came out in June 2024. If you look at the multi-head latent attention section over here, they first start out with the simplified multi-head latent attention, which is what we have seen in the previous lecture. But after this point in section 2.1.3, they introduce something which is called as the decoupled rotary position embedding. What they did in this decoupled rotary position embedding, let me go back to that section. Yeah, what they did in this decoupled rotary position embedding is that they combined multi-head latent attention with something called the rotary position embedding. And that leads to a much more powerful version of the multi-head latent attention. In the latent attention mechanism which we saw, we did not include the positional embedding, the rotary positional embedding. So to understand this advanced multi-head latent attention mechanism, we really need to understand what rotary positional embedding means. And if you see the DeepSeek version 3 paper, which came out in 2025 and which ultimately led to this whole DeepSeek revolution, it led to DeepSeek R1, etc. You will see that here they directly start with this multi-head latent attention, which by default uses rotary positional encoding or rotary positional embedding. So in this lecture, I'm going to use embedding and encoding interchangeably, but it means the same thing. So the reason we are having this 2 to 3 lectures now on positional embeddings or positional encodings is that we ultimately want to understand what rotary positional encodings are, and then we'll understand how the multi-head latent attention is mixed with rotary positional embedding to create a much more advanced version of the latent attention mechanism. So the way I'm going to divide this is that in today's lecture, I'm going to introduce you to what positional embeddings are. So today's lecture, I'm going to introduce you to what positional embeddings are. And then we are going to look at two types of positional embeddings today. We are going to look at integer positional embeddings and binary positional embeddings. That's the purpose of today's lecture. In the next lecture, we are going to look at sinusoidal positional embeddings. These sinusoidal positional embeddings were introduced in the um, attention is all you need paper. So we are going to look at these embeddings or these encodings next. If you scroll down in the paper, you will see that these are the sinusoidal positional embeddings. And then in the lecture after that, we are finally going to look at rotary positional embeddings, which will help us understand how these rotary positional embeddings are mixed with latent attention. The reason I want to go through this sequential procedure is, again, I want you to know every single thing from scratch. So if we directly start with rotary positional embeddings, some understanding, some concepts will be lost. I want to take you through how these advancements were actually discovered. So I'll go from step number 1 in today's lecture to step number 2 and then to step number 3. Alright, so let's get started with today's lecture, in which we will cover these three things: introduction to positional embeddings, integer positional embeddings, and binary positional embeddings. Alright, so the first thing is, what are positional embeddings, and why do we need positional embedding or positional encoding in the first place? The main reason is that the position at which a word comes in a sentence is very important to the context of the sentence. Let me clarify this. So, if there is a sentence called "the dog chased another dog," okay, and there are two dogs here, right? Let's say I do not consider positional embedding or positional encoding at all. What does it mean I do not consider positional embedding? Well, it means that usually in the input block of the transformer architecture, let me mark this with a different color. In this input block of a transformer architecture, when a given input text comes in, it's first tokenized, it's converted into token embeddings. We add positional embeddings to the token embeddings, and that leads to something called as the input embeddings, which is then passed to the transformer block. So let's say we don't have this positional embedding layer at all, and we just have the token embeddings. And let's say if I pass in now this sentence, "the dog chased another dog," I've passed in through the input block. What will happen is that both of these dogs will get converted into token embeddings, right? So the token embeddings are same for these two because they are the same words. So the token embedding for the first dog is this, the token embedding vector for the second dog is this. Both of these are completely identical vectors. And now both of these vectors will pass just like that to the transformer block without adding any kind of a positional embedding. This means that for these two tokens, the input to the transformer block is exactly the same, which further means that when we come out of the attention block and when we get the context vector, so we get the context vector for the first dog and we get the context vector for the second dog, dog number 2, and this is dog number 1. These two context vectors will be exactly the same because now the input to the transformer block for these two dogs is exactly the same. So they'll go through the exact same operations in the transformer block, and the context vector for these two dogs will be exactly the same. And this is not what I wanted at all, because I wanted my transformer block to actually capture the fact that these two are different dogs. I don't want my transformer to think that these are the same dogs. I want the context vector for this dog and this dog to be completely different, right? That's why position is very important. If we don't use positional encoding, the attention mechanism output for both these dogs will be exactly the same. That's not good. After coming out of the attention block, we want the model to understand the context of the sentence. We want the model to understand that the first dog who is chasing is different from the second dog who is being chased, right? So before we enter the transformer block, we want to create some distinction between this dog and this dog. And the way we do that is by adding another vector to the token embedding vector, and that's this positional embedding vector right over here. So there is a very nice tutorial on Hugging Face. What they do is that they take the same example, the dog chased another dog, and they pass it through a pre-trained Llama 3.2 architecture. What they do after passing this sentence through this architecture is that they let this sentence go through the attention block without positional embedding. So they only take the token embedding, they don't add positional embeddings, and then they compute the output vector or the context vector of both of this dog 1 and dog 2, and then they print is it identical, and they get that the context vector for both of these dogs is identical. And here they conclude that without any positional information, the output of a self attention operation is identical for the same token. That's not good at all. We want the output of the attention mechanism to be different for different tokens, right, which are in different positions, because these dogs mean completely different things. That's why position embedding or positional encoding is very, very important. So another example of this is that the dog chased the ball. It could not catch it. Now see what's happening here. If we don't use positional encoding, this it would be the same as this it, right? But that's not good because this it actually refers to the dog and this second it refers to the ball. So I want the transformer block to know that the input embedding for this it and this it is different. So they can refer to different things. That's why it's very important to somehow add the positional embedding information to the token embedding information. We need to let the transformer know at which position that given token comes into the picture, right? So that's the first takeaway from today's lecture, that positional embeddings are very important along with token embeddings. If we don't have positional embeddings, two words which look the same, if they are in different positions, they will be treated the same way by the transformer, which is not good because words which look the same can refer to completely different things. Great. Then let's start thinking about how do we do positional embedding, right? How do we do positional encoding? One more goal of mine for today's lecture is for you to start thinking from first principles. So pause this video for a moment and think that, okay, let's take the same example, the dog chased another dog. And you have got the token embedding and you somehow want to add a positional embedding vector to each of these token embedding vectors. How will you encode the information about the position? Think about this for a moment. You can pause this video also. All right. So the simplest way to think about this is that, okay, if I want to encode the position information, let me just do this. Let me take the position number of this token in the sentence. So this dog comes at position number 2 and this dog comes at position number 5. That's it. I'll just use these positions and add it to my input embedding vector. So the way I'll do that is that if the embedding size is equal to 8, let's say, and if dog comes at a position number 200, I'll just use 200 and then I'll create 8 copies of it. So the positional encoding vector for dog will be 200, 200, 200, 200, 200, 200, 200, 200. And then I'll just add it to the token embedding vector. What will be the problem with this? First, let me explain to you how this will work in practice. If we take the sentence, the dog chased another dog, right? Let's take a look at the first dog in this sentence. So, in the whole input context, if the first dog comes at position number 200, we'll assign it a value of 200. So, this will be 200, chased will be 201, another will be 202, and the second dog will be 203, right? So the first dog will, so every value here will be now repeated 8 times because that's the size of the token embedding vector and we need to add both of these vectors. So the first dog will be 200 repeated 8 times and the second dog will be 203 repeated 8 times. What's the issue with this approach? What's the problem with this approach? We are achieving what we set out to achieve, right? What I wanted to achieve was that I wanted the transformer to know that the input embedding vector for this dog and this dog is different. That's what we are achieving. For the first dog we are adding a vector of 200s, for the second dog we are adding a vector of 203s. So the input embedding vector, which is the sum of the token embedding plus position embedding, will be different for the two dogs. So if we are achieving what our original aim was, what's the main problem with integer positional encoding? Well, the main problem with integer positional encoding is the magnitude of the values itself. So if you look at token embedding values and the way token embedding values are usually initialized in large language model architectures is that these values are usually clustered around 0, which means that these values are usually small, right? On the other hand, if I have a context length of 1024, let's say, I'll have these positional embedding values which are very large. So if you add a very, very small value to a huge value, what will happen? The effect of this smaller value will get completely vanished and it will be mostly dominated with this positional information. That's not good at all. Token embeddings play a very important role. Token embeddings capture the semantic meaning of words, and I don't want that information to be diluted. I don't want that information to be lost. Um, so, if the integer positional encoding values can be very large, right? So, we add a very high positional values to the very small token embedding values. What this does is that this heavily pollutes the semantic information which is captured by token embeddings. And that defeats the whole purpose of token embeddings because we capture the semantic information which is then passed to the transformers, right? What does capturing semantic information means? It means that words which are similar, such as let's say kitten, words which are similar will lie together in vector space, whereas words which are dissimilar, like if there is a plane here, that will lie somewhat different from these other vectors. So token embeddings encode semantics. So now if you take these token embedding vectors and you add a positional embedding vector suddenly, which is a huge value, these token embedding vectors will get their information will get diluted. They won't play such an important role, which is not good for us. We want this information also to be retained. So ideally, what we want, along with the fact that I want to tell the transformer that this dog is different than this dog, so they should have different values, different positional values. I also want to make sure that the positional encoding values need to be constrained and they should not be very high. So now think about this, right? What can you do to make sure that the positional encoding values are constrained, hopefully between 0 and 1, let's say. So I'll use the same logic. Let's say I have these positions 200, 201, 202, 203. How can I represent them in a vector so that every value of the vector is constrained, hopefully less than 1? How will I do this? Again, think about this for a moment. I'm going to pause here for a while. So this is where binary position encoding actually comes into the picture. The main idea is that integers can be unbounded, right? They can take very large values. So if I want these values to be constrained, why don't I represent every value by binary numbers? What that means is that let's say instead of 200, so the position value for the first dog is 200, right? What if I represent it as a binary representation whose size is equal to 8, which is the exact same size as the token embedding or the token encoding vector? So now you see that if I'm going to represent 200 with the binary encoding value, then suddenly the representation becomes 11001000, right? And then each value here is constrained to be less than 1. It's either 0 or 1. So it's the order of magnitude now of the token embedding vectors. The order of magnitude of the token embedding vector and the position embedding vectors are around similar. That's great for us. This is exactly what we wanted, right? So what we'll do here is that if we have 200, 201, 202, 203, etc., all of them will be converted into binary representations. So let's see what that actually means. If you have, let's say, we are looking at an input sequence whose positions go from number 64 to 65 to 75. The way each of these tokens would be represented, so the way their positional embedding vectors would be represented will be like this. If you look at 64, It will be represented like this. If you look at 65, it will be like this. We use a different color. If you use 60, if you see 66, it will be like this, etc. So every position here will be represented with a 8-dimensional vector. Now I want you to observe some very key things over here which will play a very important role when we are looking at sinusoidal position embeddings and eventually rotary positional encodings. One key thing to realize here is that there are two things, right? The first is the position itself. Here the position is 64, 65, 66, 67, and within each position I have actually index, right? So within each position, I have index number 1, index number 2, index number 3, index number 4, index number 5, index number 6, index number 7, and index number 8. So whenever I am going to refer to index or indices in this lecture and in subsequent lectures of positional encodings, it means these digits, right? So this index is called as the least significant bit, LSB, and this first index is called as the most significant bit, MSB. And I have also mentioned that this is LSB and this is MSB. And I have also mentioned that over here, if you look at 64, we have index 1, 2, 3, 4, 5, 6, 7, 8. Index 1 is called the LSB, least significant bit. Index 8 is called as the MSB. Now I want you to notice a couple of observations over here. Take a look at the lowest index over here, which is this index number 1. And let's see how it oscillates, right? We'll start from the top. We'll start from 64 and take a look at this lowest index. You'll see it goes from 0 to 1, 1 to 0, 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 which means that it's oscillating the fastest, right? Now let's take a look at the second index here. So it's the same for first two values 0 0, then it changes 1 1. So its oscillation frequency is slightly lesser, right? After every two values it's changing. Then let's look at the third here, which is shown by the yellow. If you take a look at the third one, for the first three values or for the first four, it's the same. So for the first four, it's the same. Then for the next four, it's the same. Then for the next four, it's the same, etc. So what I'm trying to show here is that lower indices oscillate fast between positions. You should understand what this sentence mean. What does this mean? Lower indices oscillate fast with respect to positions. What this means is that lower indices means, let's say we look at index number 0. Index number 0 oscillates the fastest, right? It quickly oscillates as I move from different positions. Whereas if you move to higher indices, they don't oscillate too much at all. In fact, take a look at the seventh index. The seventh index is same across all, right? So it does not oscillate at all. Take a look at the third index. The third index oscillates after every four positions. The third index oscillates after every four positions, but the first index oscillates after every position, so it oscillates the fastest. Why am I telling you this? Because later we are going to see that the lower indices oscillate the fastest, right? So they capture fast changes among positions, and the higher indices oscillate very slow. So for the higher indices, they do not capture fast changes across the different positions. This is the same concept of indices and positions which ultimately led to sinusoidal position embeddings, right? So there are a few observations which I've made here. The first index oscillates between, let me show this with a different color. The first index oscillates between 0 and 1 with every new position, as we can see over here. The first index oscillates between 0 and 1. The first index oscillates between 0 and 1 for every new position. That's done. I've shown this with the red color over here. Okay. The second index oscillates between 0 and 1 with every two positions, which is shown by this purple color here. It oscillates after every two positions. This is also done. The third index oscillates between 0 and 1 after every four positions. So this let me change, or let me clean some color over here. So third index oscillates between 0 and 1 after every four positions, right? So this is also done. Similarly, in the eighth index oscillates between 0 and 1 with every 128 positions. That's why it does not oscillate from 64 to 75. This eighth index over here. This seventh index oscillates between 0 and 1 every 64 position. So now let us write the oscillation frequency for all of these positions, right? The first index oscillates between 0 and 1 every 1 position. Second index every 2 position. Third index every 4. Fourth index every 8. Fifth index every 16. Sixth index every 32. Seventh index every 64. And the eighth index after every 128 positions. So that's why you'll see that since we are only showing 11 positions over here, these indices won't oscillate. These indices won't oscillate in the example which I've 64 to 75 which I've shown, because they oscillate every 16, 32, 64 and 128 positions. So if you plot the oscillation frequency versus the index position, you will see that the index position 1 has the highest frequency and then the oscillation frequency actually goes down, right? So the lower indices actually capture immediate changes across the different position values, whereas the higher indices capture small moving changes across the different position values, which means that position number 1 and position number 8 now, so the higher index position will not change unless we jump 128 positions. So if you have a sentence and nearby tokens are, or there are nearby tokens which are the same, um, which have the same word, but they are spaced out by a factor of 3 or 4, which means they are close by. Their differences are mostly captured by the um, lower indexes, because the lower indexes capture faster oscillations. So, one more graph which is extremely important, which I want to show you now, is this particular graph, right? And let's try to understand this graph in detail. So, you'll see that on the x axis, I've shown the position, and that can be any position here, 64, 65, 66, etc. And for every position now, we have 8 indices, right? Index 1, index 2, index 3, 4, 5, 6, 7, 8. So the way to interpret this graph is look at a position, and every position has 8 different indices now, 1, 2, 3, 4, 5, 6, 7, 8, which are the values between 0 and 1. What this particular plot shows is that how the different index values oscillate. So you see the first index oscillates very fast, right? After every position change, it oscillates. Here we saw this directly. Even with one position change, it oscillates. So that's why the frequency of oscillation of index 1 is the highest. The frequency of oscillation of index 2 is slightly lower. It oscillates after every 2 positions. Index 3 oscillates after every 4 positions. Index 4 oscillates after every 8 positions. Index number 5 oscillates after every 16 positions. Index number 6 oscillates after every 32 positions. Index number 7 oscillates after every 64 positions, and index number 8 oscillates after every 128 positions. I hope you have understood this graph, because this is the same graph which we'll be seeing in the sinusoidal positional embeddings as well. Okay. So what we have shown in this graph is that we have considered two factors, the position of the token and the index number. These two factors will later show up in sinusoidal positional encodings and rotary positional encodings as well. So higher, the main conclusion from these so far is that the higher indices, or I should say the lower indices, so this should be lower indices over here, change more frequently, suggesting fine-grained encoding, which means that fast changes in nearby positions. And the lower index and the higher indices, so here I should say higher indices change less frequently, meaning coarse encoding, and that means that they don't capture minute changes in positional encoding. They capture broad level changes. I'll explain the intuitive meaning of this when we come to sinusoidal encoding in the next lecture. But for now, just remember that lower indices change more frequently. And let me actually just change this in front of you so that uh, we are all able to see this. Oops. So what I want to do over here is that I want to change this to lower, because this should be lower indices change more frequently, and this should be higher, which should be higher indices change less frequently. And then I'll again add a box around this. All right, now it seems to be correct. So it seems that with integer positional embedding, we have solved the issue of the with binary positional encoding. We have solved the issue with integer positional encoding, right? We have values which are now bounded. They are either zero or one, and of course, because every position has different values, we take care of the first problem which we thought about, that different positions should have different values that needs to be added to the token embedding vector. So what's the main problem with integer encoding? Can you try to think about this for a moment? You can also pause this video here for a while. One of the main problems of integer positional encoding is this graph. You see, the issue with this graph is that there are discontinuities, right? The values of integer positional encoding are discrete. They are either 0 or 1, and they lead to discontinuities in the resulting vectors. So during pre-training, it becomes difficult for the LLM optimization. Remember, what's going to happen is that we don't know these positional encoding values from the start. We are going to pre-train these values along with all the other parameters of the LLM. So during pre-training, it becomes difficult for the language model to deal with these jumps. It becomes difficult for the language model to deal with these jumps. So backpropagation becomes harder. So ideally, what would be the best for us is that we have a graph similar to what we are seeing over here, but the values are smoother. Can we have a graph like this? Can we have a graph like this where the values are smoother and the values are not discontinuous? And immediately that suggests an intuition for us, right? If we want values which are smoother but not discontinuous like this, what if we have sine functions, or what if we have cosine functions instead of these discontinuous values? And that eventually brings us to the next type of encoding, which is sinusoidal positional encoding, which we are going to cover in the next lecture. So far, what we have seen is that we have seen that there are two types of positional encodings which we have seen in today's lecture. First is integer positional encoding. The major issue with integer positional encoding was that the values were not constrained. So the positional encoding values were far higher in magnitude than the token encoding values, and they diluted the information given by the token encoding, which is not good. Token encodings capture the semantic meaning, and I want that information to be retained. So ideally, we want these values to be bounded. So then we started thinking that if we want these values to be bounded, why don't we have a binary encoding for every value? So if it's 200, let's represent it with a binary representation. And once we represent it like this, it constrains the values, but it opens the door for new interpretations, which means that now what I can do is that I can have two variables. I can have my position on the x-axis, which is the position of that token in the context. And then on the y-axis, I can have index number 1, index 2, 3, 4, 5, 6, 7, 8. Right? These are the different indices. And then I can actually plot how different indices change with my position. So the lower indices, index 1 and 2, change very fast, whereas higher indices actually change very slow. This indicates that the lower indices are actually capturing something different than the higher indices, right? The lower indices capture quick changes in my positional encoding values, whereas the higher indices don't capture these quick changes. We are going to see what every index means and why are we looking at this visualization later when we look at sinusoidal and rotary positional encodings. But just remember that this graph opens a door for new visualization, index and position, and we can plot this oscillation frequency. The main issue is that these are not continuous values, right? These are completely discrete values, which means that there are jumps, there are discontinuities which are not good for backpropagation. That's where sinusoidal encodings come into the picture, where what sinusoidal encodings actually propose is that why don't we have why don't we make this smooth and continuous like this? So then it should also be differentiable, and then backpropagation will be just much more easier. These sinusoidal encodings were exactly what was proposed in the Attention is All You Need paper. What you see over here are these sinusoidal positional encodings. So from this paper, it's very difficult to understand why this is exactly proposed. But to truly understand this, you need to go through this whole exercise of first there was integer positional encodings, then we have binary position encodings. Then we saw that this is fully discontinuous. So then why don't we make it continuous? Then why don't we come up with sinusoidal positional encodings? So once you go through positional encodings in this manner, things become a lot more easier than just going through this formula, which is very tough and very difficult to understand if you don't have any background. So these people, they just have two paragraphs, two or three paragraphs on this. But to unpack this, we are going to do this in 2 to 3 lectures. Rotary positional encodings came after this actually. So in the next lecture, we are going to look at sinusoidal positional encodings. That will be a full lecture because it's a very detailed concept. And after that, we are going to look at rotary positional encodings, which will eventually help us understand how multi-head latent attention was mixed with rotary positional encoding. We'll also need to see why people now use rotary positional encodings much more commonly than sinusoidal positional encoding. Thanks a lot, everyone, for attending this lecture. Positional encodings is one such topic which is very non intuitive. So it's very difficult to understand, at least for me, it was quite difficult to understand this formulae. Only when I went through this step by step understanding of let's start thinking from first principles and how might positional encodings have been derived. If I were to derive this first, I may have started with integer, then binary, then I would have moved to sinusoidal. And then when we learn sinusoidal and when we truly understand it, that provides us a very nice clue or a hint to go to rotary positional encoding, which we are going to see in tomorrow's lecture. Thanks everyone, and I look forward to seeing you in the next lecture.